These are the answers to homework 4D. First, the definitions. Now to the questions. Number 1, for each of the following reactions, specify whether it is an oxidation-reduction reaction or not, and then if it is, identify the element oxidized, the element reduced, the oxidizing agent, and the reducing agent. In order to determine if a reaction is an oxidation-reduction reaction or not, you have to see if one element has its oxidation number going up and another element has its oxidation number going down. So it requires calculating oxidation numbers for all the reactants and products. Elemental copper has an oxidation number of 0. Silver ions have an oxidation number equal to their charge of +1. Copper ions would therefore be +2, and silver atoms would be 0. In this case, we have the copper atom going from a charge of 0 to +2, it's being oxidized. The silver ion is going from a charge of +1 down to 0, it's being reduced. So this is an oxidation-reduction reaction, and it's the copper that's being oxidized because its oxidation number is going up. And whatever reactant has its oxidation number going up, that's the reducing agent, so copper is the reducing agent. The silver ion is being reduced down to elemental silver, so silver ions are being reduced, and the silver ion is the oxidizing agent. Notice the agents always come from the reactant side, so that's why I wrote silver ion, not silver atom. For the second reaction, the hydrogen's oxidation number is +1, chloride is -1 in HCl. In NH3, the hydrogen is +1, the nitrogen is -3. And in ammonium chloride, the hydrogens are +1 each. The chlorine is -1, nitrogen has to be -3. In this particular reaction, all three elements maintain the exact same oxidation state on the left and the right side. This is not an oxidation-reduction reaction. This is a non-oxidation reduction reaction. For C, in the first compound, chloride is -1, silicon is +4. In water, hydrogen's +1, oxygen's -2. In HCl, hydrogen's +1, chloride's -1. And in SiO2, the O's would be -2 each, so the silicon would have to be +4. All four elements in this reaction maintain the same oxidation state from the reactant side to the product side, so it is not an oxidation-reduction reaction. In D, silicon tetrachloride, chlorine is -1, silicon's +4. Elemental magnesium would be 0. In the compound MgCl2, magnesium is +2, chloride's -1, and elemental silicon is 0. In this case, we have the magnesium going from a charge of 0 to a charge of +2, so its charge is going up, it's being oxidized. And the silicon is going from +4 down to 0, so it's being reduced. So we have an element being oxidized and an element being reduced. This is a redox reaction. The magnesium is the one that's being oxidized, so it is the reducing agent. And then the silicon that is on the reactant side, the +4 silicon, is what's being reduced. And so we would either say the silicon +4 is the oxidizing agent, or when they talk about agents, they'll sometimes say the entire compound. So SiCl4 would be considered the oxidizing agent for reaction D. Problem number 2, predict the products of the following oxidation-reduction reactions, but do not balance them. First one, solutions of potassium dichromate and sodium sulfite are mixed. If you switch the partners, you're going to get two compounds that each have alkali metal ions in them, which means they're both soluble. So this is not an obvious reaction. You cross that out, go to Plan 9, write the reactants in ionic form. If the reactants, when written in ionic form, you can recognize a strong oxidizing agent, then this will be a non-obvious oxidation-reduction reaction, and this is what you should recognize right here. The dichromate ion is a strong oxidizing agent, so it's going to oxidize something else in this reaction. In order to figure out what it oxidizes, we write the oxidation numbers. Potassium is +1. In dichromate, chromium is 6, oxygen's -2. The sodium ion is +1. And in the sulfite ion, oxygens are -2 each. They add up to -6, so the sulfur would have to be +4. So what you need to know is what the strong oxidizing agent preferentially turns into. The dichromate ion is going to be reduced into the chromium 3 ion. So its oxidation state is going from 6 to 3. That's the reduction. You have to find one of the other elements whose oxidation numbers can go up. Potassium can only be in its elemental form or a +1 ion. It can't go any higher than +1. The oxygen is almost never the element being oxidized because it's the second most electronegative element on the periodic table, so it's usually best just to ignore the oxygens. Sodium can be 0 or +1, so it can't go any higher. But the sulfur has an oxidation state of +4, and sulfur's highest oxidation state will equal how many valence electrons sulfur has, which is 6. So sulfur can go as high as +6. So this must be the element that's going to be oxidized. And what it's going to be oxidized into comes from the fact that the sulfur is in the sulfite ion. And if it's an ITE ion being oxidized, it gets oxidized up to an ATE ion. So you're going to produce sulfate. So the final equation, not balanced, but predicted products, would be dichromate ion plus sulfite ion yields chromium 3 ion plus sulfate ion. B, carbon monoxide is bubbled into an acidified solution of potassium permanganate. We have two compounds here, and we can try to switch the partners, but we're not going to wind up getting a precipitate or water, so this is not going to be an obvious reaction. Must be a non-obvious reaction then. So we go to Plan 9, write the reaction in ionic form, and the type of non-obvious reaction we're going to look for is going to be based upon the fact that one of the reactants is the permanganate ion, and that's a strong oxidizing agent. So this is not going to be a Bronsted acid-base non-obvious reaction. It's going to be an oxidation reduction non-obvious reaction. The only thing you dissociate into ions are soluble ionic compounds and strong acids, so I leave the carbon monoxide molecule bonded together. It's actually written accurately that way. But the potassium permanganate solution would actually be dissociated into its two constituent ions. If we want to predict what the permanganate's going to oxidize, we need to calculate the oxidation states of all the elements in the reaction. Oxygen in carbon monoxide is -2, so the carbon must be +2. Potassium is +1. And in the permanganate, the manganese is +7, the oxygen is -2. If this is an acidic solution, the permanganate ion always gets reduced to manganese +2. Its oxidation state is going down from 7 down to 2. So something has to be going up. And the one that can go up is the carbon. Carbon has 4 valence electrons, so its maximum oxidation state can be +4, but right now it's only +2. So it's going to be oxidized up to +4, and the only way you're going to get a carbon as a +4 is if it bonds with 2 oxygens and produces the gas carbon dioxide. So the final reaction would be carbon monoxide plus the permanganate ion yields carbon dioxide plus manganese 2 ions. C, a basic solution of potassium permanganate is mixed with a solution of tin 2 nitrate. Two compounds reacting. For the obvious type of reaction, you would switch the partners, but when we switch the partners, we don't get a precipitate, we don't get water, so that didn't work. It must be a non-obvious reaction. Plan 9, write the reactants in ionic form, and if you recognize a strong oxidizing agent, which we do in this case, there's the permanganate ion, this is going to be a non-obvious oxidation reduction reaction. Let's do the oxidation numbers. Potassium is +1. In the permanganate ion, manganese is 7, oxygen is -2. The tin 2 ion is +2. And in the nitrate ion, the O's are -2 each. They add up to -6, so the nitrogen would have to be +5. Now, this reaction is occurring in a basic solution, so the permanganate ion actually gets reduced down to a +4 oxidation state, then precipitates out with oxygens. So it forms manganese 4 oxide as a solid. It's still a reduction, so we always know what element's being reduced. The thing you have to do is figure out what element can be oxidized. Potassium can't go any higher than +1. Nitrogen has 5 valence electrons, can't go any higher than +5. But tin is in the 4th tall column on the periodic table. It can actually go as high as +4, so the tin 2 ion must be oxidized up to tin 4. So the reaction is permanganate ion plus tin 2 ion yields MnO2 solid plus the tin 4 ion aqueous. And this would be correct if it wasn't for the fact that this is in a basic solution. And basic solutions contain hydroxide ions. So anytime you predict the products in a basic solution, check to see if you have a product that's a cation, because many cations on the periodic table will precipitate with hydroxides, and tin will. So the tin will actually bump into those hydroxide ions eventually in that solution, And every time it hits a hydroxide, it's going to stick, and you're going to wind up sticking 4 hydroxides onto that tin. And so the second product is going to actually be tin 4 hydroxide solid as opposed to tin 4 ions aqueous. D, concentrated nitric acid is added to a solution of sodium bromide. 2 compounds, you can switch the partners, but you don't get a precipitate, you don't get water, so go to Plan 9, write the reactants in ionic form. Nitric acid's a strong acid, that's why we ionize it. Sodium bromide, a soluble ionic compound, that's why we dissociate it. This contains concentrated nitric acid, which is a strong oxidizing agent. So this is not going to be a Bronsted acid-base reaction. It's going to be an oxidation reduction reaction because it has concentrated nitric acid. So let's do the oxidation numbers. Hydrogen's +1 in the nitrate ion, nitrogen's +5, oxygen's -2, sodium ions +1, bromide ions -1. The nitrate in the concentrated nitric acid gets reduced into the poisonous orange gas, nitrogen dioxide. So the nitrogen's oxidation state has gone from +5 down to +4. That's gone down. You have to find one that can go up. Hydrogen can't go any higher than +1. Sodium can't go any higher than +1. But if you ever have an anion of a nonmetal, they'll be negative. They can always go up to their elemental state of 0. So the bromide ion is going to be oxidized up to elemental bromine, which is going to be Br2, and elemental bromine at room temperature is a liquid. So the final reaction is NO3- plus Br- yields NO2 plus Br2. Of course, none of these have been balanced yet. We haven't learned how to balance those. That's going to wind up being the next lecture. But as long as you can predict the products now, that's what we're looking for. Let's try the last one. E says aluminum metal is added to a solution of hydrogen peroxide. So aluminum metal with hydrogen peroxide, when you see hydrogen peroxide, you recognize that's one of our strong oxidizing agents. So I would immediately think this is going to be a non-obvious oxidation reduction reaction. If I write the reactants in ionic form, nothing changes. Elemental aluminum is already written correctly, and hydrogen peroxide is like a molecule like water. It stays bonded together in solution, so we leave it like this. To calculate or figure out what's going to happen, we'll do the oxidation numbers. Elemental aluminum is 0, and in the hydrogen peroxide, the hydrogens are +1 each, and the oxygens are -1 each. We know what the oxidizing agent turns into. Hydrogen peroxide turns into water because the oxygen goes from -1 down to its more stable state of -2. That's your reduction. The only thing that can be oxidized is the aluminum. And aluminum can be oxidized up to its only other possible state, which is +3. So the predicted products would be the aluminum atom reacting with hydrogen peroxide to form aluminum ions and then liquid water.